Okay, hi. So the definition of a sequence is a list of numbers, algebraic terms, shapes, or other mathematical objects that follow a pattern or rule. Okay, so with a sequence, we have these things that, this thing that's called the nth term. And the nth term basically defines how you find each term of the sequence. Now, in another video, I'll cover how to actually find the nth term for sequences, both linear and quadratic. But today we're just going to be learning about the nth term, but not actually how to calculate it. So I'll give an example of a sequence. So first off, we have linear sequences. So linear sequences are your most basic type of sequence that we'll be learning about, which is when you have numbers that go up with a common difference. So there's a common difference here, which is that each term in the sequence is increasing by 4. And that, so we call the common difference, we say the common difference is equal to 4. Okay, so the common difference can also be negative. Consider something like this, minus 3, minus 6, minus 9, etc. So now we can see that the common difference is actually a negative. We're subtracting by 3 each time. So our common difference is minus 3. Okay, and the nth term for these sequences, for example, for this top one, the nth term would be 4n minus 1. So again, we'll go over calculating that in another video, but that is the nth term. And the reason I'm bringing it up is because you can put in any value, any integer value of n, and you'll get a value for the sequence. And it actually corresponds to each term in the sequence. So if you put in n equals 1, you'd get 4 times 1 minus 1, which is 3. So that works. And then if you put in, for example, 4 times 5 minus 1, we'll get 19. And you can see that it works because the 1 gives you a 3 and the 5 gives you a 19. So that's basically how we can set this expression to define what you're going to get out of the sequence depending on which term you put in, right? So the second type of sequences we need to know about are geometric sequences. And geometric sequences work like this. So you could have something like this. Now this is a little bit complicated, but in essence, all we're doing is instead of adding by a number, we're multiplying by a number, multiplying by 3 every time, like so. And since we're multiplying by 3, instead of saying the common difference, we call it the common ratio, and that's 3. Okay, and this goes on forever. And again, the common ratio can also be division as well. Now, another geometric sequence would be this. So these are powers of 2. If you think about it, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, and so on. So what we can do is we can put the nth term in the form r to the power of n. I'll put that in red. So r to the power of n is how we figure out the nth term in this scenario, where r is our first value here. So that would be 2. And then obviously n is just whichever term in the sequence you want to pick. So if we pick if we picked n equals 5, then we get 2 to the 5, which would be 32, which would be correct according to the sequence. Right, another interesting use of this equation is when we're multiplying by surds. Now, the thing is, what we could do is, if we had a sequence like this where we're multiplying by √3 each time, what we can say is that if you think about it, √3 times √3 is just 3. Because remember, when we multiply two roots together, we can take the root away because it's √3 squared. So we'll just get 3. And then when we multiply by √3 again, we get 3√3. And then when we multiply by √3 again, the √3s, again, we can turn into a 3. So we get 3 times 3, which is 9. And another way to see this is if we put it in this form again with r to the n, our r now is √3, and we have to the power of n. So for example, if we wanted to figure out n equals 3, or 4, let's say, we just put in 4 as n, and then we can say that that's the same as √3 or 3 squared, which is 9, for example. But just to clarify, for this third term here, we have 3√3 times by √3. And what we can do is we can change this to be 3 times by 3 √3 squared. Or we can write it like this, for example. So 3√3 times √3 is the same as 3 times √3 times √3, because remember, this 3√3 just means 3 times √3. And then we can just, because we have √3 times √3, we can rearrange that to be √3 squared. We know that the squared cancels out with the square root. So we end up getting 3 times 3, which is 9. And that's how it works. All right. So here are some other sequences that you don't need to really know much about, but you need to know that they exist. So we have triangular numbers. And triangular numbers can basically be represented as triangles. So our first term of the sequence is 1. Our second term is 3. Our third term is 6. And our fourth term is 10. And so on. And basically, you can see that because the reason they're called triangular numbers is because they form triangles. And what happens is that you add 2, then 3, then 4, and then 5, and then so on. You can see because you add a row of 2 the first time, then a row of 3, then a row of 4. That's how it works. And if we wanted to, we can also just show that which term of the sequence we're dealing with here. The nth term you don't need to know, but if you want to know, this is the nth term of triangular numbers. Another more familiar one will be square/cube numbers. So square numbers are just your perfect squares, and then you also have your cube numbers. So these ones might be less familiar, but this will be 2 cubed, this will be 3 cubed, 4 cubed, and so on. And you can see that n equals 1, 2, 3, 4, 5. And the nth term for square numbers is n squared, and the nth term for cube numbers is n cubed. Because again, if you put in a value of 3, let's say, to the square numbers, you're going to get 3 squared, which is 9. And if you put it into the cube numbers, you're going to get n cubed, which is 27. And then finally, we have, I'm just going to make a little note here. Fibonacci numbers. It's called the Fibonacci sequence. It's a very famous sequence where you have it basically like this. It might look less obvious to you what the sequence is here. But if we look, what it's basically doing is the first 2 terms are 1, and then every term after that adds together the 2 previous terms. So the third term adds the first and second term, so it would be 1 plus 1, which is 2. The fourth term adds the second and the third term, so it's 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. So that's how the Fibonacci sequence works, and you don't need to know the nth term for this. But you don't need to know the rest of these nth terms. That's why we're not calculating them for them, but they're just there if you're curious. So yeah, another thing is finding the nth term. So actually calculating the nth term, which again we'll do in a different video. But the only ones you have to know how to calculate are the linear terms, the linear sequences, and quadratic sequences, which we'll move on to.